Chaturani Dias from the Center for Biomedical Innovation in University of Moratuwa, and I will be supporting today as one of the moderators of the day. So to begin today's workshop, I would first like to thank the Makerspace Program for developing this platform to connect the tech experts and the tech enthusiasts of our country to share their knowledge. So I'm excited to welcome all the speakers who have joined today. I'm excited to welcome all the speakers who have joined with us today. Thank you very much for your presence, and all the organizers of this event for making this possible. And a warm welcome is extended to all the participants who have joined with us today. Before we quickly go into the workshop, I would like to introduce Engineer Kitmi Mawella, who will be joining as the moderator during question and answer sessions. She is a research scholar of the Department of Mechanical Engineering, as well as the Bionics Laboratory in University of Moratuwa. A quick few notices as well. All the participants are invited to share your questions of each session in the chat. And the moderator will be presenting them, organizing and presenting them to the speaker at the end of each session as best as time permits. There will also be a design challenge from this workshop, which will be introduced to you during the last session for today by Engineer Pubuduranavira. So you're invited to stay with the workshop and participate in this design challenge as well. So without further ado, I would like to invite all of you to the first session of today, the welcome and introduction to the workshop by Dr. Gayani Nandaseri of University of Moratuwa.
Okay, thanks, Chaturani. So I will first share my screen. Thereafter, I'll start my talking.
Yes, Dr.
Okay, so good evening, everyone. So I would like to welcome you all here to the two-day online workshop on Bionic Limbs, Shaping Humanity Using Technology. So this is a part of the Advanced Tech series, as mentioned earlier. So this is partly, conducted by the Bionic Labs of the Department of Mechanical Engineering, University of Moratuwa, in collaboration with the Center for Biomedical Innovation, University of Moratuwa. So I am Gayani Kashmira Nandasiri, the workshop coordinator for the Center for Biomedical Innovation, University of Moratuwa. So today's workshop actually aims to provide knowledge on artificial limbs and prosthetic technologies available to assist the human beings who are in the need. So further, it is actually aimed to share the research and developments conducted in this area, including the success stories to encourage further research. So the partners for today's workshop are the Bionics Lab from the Department of Mechanical Engineering and the Center for Biomedical Innovation, University of Moratuwa, American Center, the Imperial College London, UK, Kyushu University, Japan. So I would first then let me walk through the first day of the workshop. So our first speaker will be talking on how the Bionics Lab limbs are improving the lives, which is one of the most important facets of these technologies to improve the quality of life of people. Thereafter, our next speaker would be going on to talk about the design process of the Bionic Limbs, in which he would be focusing on how this need could be converted to an aid, which will unfold many technical details. Now, looking at this interesting presentation lineup, I'm sure that it is going to create many questions from you. So we will try to answer as much as possible from my end. So you can, as Chaturani said, you can direct the questions to the chat box. So our team will try and answer as much as possible. So if you require any further technical clarification from our speakers, so the moderator will actually direct those questions to the dedicated question and answer session in each section of the workshop. So So thereafter, I would actually, then finally, we would introduce the Makerspace Design Challenge to you, and then we will wind up the session for today. And then for the next day, we will start from the muscles for communication, muscle signal-based control of the bionic limbs, and then we will move on to the brain signal-based control of the bionic limbs, which is simply put in short with move it with your mind. And then finally, we will have a session with a few success stories of us, few of the scientists. So which is to actually aim towards aspiring young scientists, maybe in the crowd today, or hopefully tomorrow you will also join. So the success stories would actually to inspire you to do further research on this area. And then we will finally wrap up the session with any closing remarks and thoughts. So then I would like to actually give you a brief introduction into who we are. So the Center for Biomedical Innovation, normally referred to as CEBI, is a multidisciplinary research center established for biomedical product development and commercialization. It was established in 2017 with the vision to be the South Asia's premier research hub for the biomedical devices. Now, the focus of the center is on biomedical innovation and product development for Sri Lanka as well as for the region. So CEBI would be acting as an intermediary in between the inventor and the manufacturer to help the design and development of the prototype to a product. So even though the product development is our primary focus, it will not be the only outcome of what we do. So there are publications, prototypes, patents. Also, the center would like to extend the interest into the biomedical research as well as for the biomedical education. So our team includes working committee members in 7 engineering disciplines and members in the medical and business sector. And we have local and foreign supervisory experts and research and administrative and commercial expert team. So more importantly, if you would like to connect with CEBI for collaborative projects, collaborative workshops, and for biomedical commercialization, you're more than welcome to do so. So in CEBI, the product development process in a nutshell, as is presented in this slide. So essentially, via translational research, when the product is to be developed, it comes in the form of a prototype, and then the CEBI, the center, will be there to nurture it, as I explained earlier, to develop it into the commercializable product. So our focus is actually in 3 pillars. One of which is in the diagnosis and therapeutic and the wellness. So if I may take you through a few of the projects which were there from the center's point of view in 2020 to 21. The first one is hydrogel-based food care solutions for diabetic patients. So this is actually a project on product development and commercialization funded by the World Bank Ahead Research for Commercialization. A national patent is filed, and currently the commercial partnership is in progress. The second one is a 3D printed spinal orthosis for scoliosis, which is a translational research project conducted in collaboration with the Imperial College London and the School of Prosthetics and Orthotics, Ragam, Sri Lanka. So it is focused in a clinical study as well as 3D modeling and printing technology, and also body interface pressure and force analysis. So it has led to a publication in Applied Sciences Journal. And the next one is affordable linear ring fixator for management of fractures, which is also a translational research project conducted in collaboration with the Imperial College London and also the Department of Vascular and Transplant Surgery, Colombo North Teaching Hospital. So it includes a clinical study as well as development of composites for the fixator design, which has also led to a publication in the Applied Sciences Journal. And then we have conducted few clinical validation studies, and then we have a low-cost ICU bed project going on, and then Shimmer IMU gate analytics and also for sport analytics done for the cricket. Sri Lankan cricket. So I have one video that I thought it would be easier for me to showcase some of the projects that we have already discussed. So I will play it for you.
Welcome to the Center for Biomedical Innovation. Established in year 2017, the Center for Biomedical Innovation, or CEBI for short, has been on a mission to be the premier institution to pioneer biomedical devices for commercialization within Sri Lanka and be impactful in the South Asian region.
Let's take a look at some projects the Center for Biomedical Innovation was able to complete within its 4 years. The shimmer-based IMU system was a key design done by the center. The team developed algorithms to assist in measuring gate angles, which could be used in effectively performing gate analysis using the IMU systems. These algorithms were utilized in some of our other projects as well. The Fixator project is an ongoing clinical study to check the validity of a linear fixator design in collaboration with the Imperial College London and the University of Moratuwa. Currently, CEBI is looking to commercialize the product by getting the help of a Sri Lankan partner. The ICU bed project was done in collaboration with Eastlink group of companies, where the center and the company worked together to create ICU beds for patients in need. Under the Health Management System project, the CEBI team and a group of interns consisting of second-year undergraduate students conducted a 3-week observational study. There, they identified a development roadmap for existing health information management systems in Sri Lankan hospitals. The study was done in collaboration with the Health Promotion Bureau, the Panathura Division Hospital, and the Dompe E Hospital. Under the hydrogel project, the CEBI team developed hydrogel-based insoles to be used in footwear to prevent diabetic foot ulcers. The developed insoles will promote healing by offloading and relieving pressure points under the foot, while also being suitable to treat several other foot deformities. The CEBI team is in the final stages of handing over this technology to commercial partners.
Join us and be a part of this trailblazing endeavor.
Okay, so then I would like to next move on to the Bionics Lab project. So I would like to introduce a few of the projects that has been conducted by the Bionics Lab Department of Mechanical Engineering, which would be in more details, will be explained to you in just after the my presentation by our speakers. So they have developed HiPro, which is a multi degrees of freedom hybrid transradial robotic prosthesis, and EEG controlled hand prosthesis, and trans-tibial prosthesis, which you will be introduced into the second day of the workshop. So lower extremity, the lab has also developed lower extremity exoskeleton robot for power assistant and modular power assist robotic ankle exoskeleton, and also a few hand prosthesis designs, which I'm sure now you are quite much interested in getting to know further details of. So without further ado, I would give the chance for the speakers. So more importantly, if you would like to connect with us, here we have provided the contact details for both CEBI and also for the Bionics Lab. So we would hope that you would connect with us for our future workshops, as well as you may be able to connect with us for possible collaborative projects. So without taking further time, I would like to say thank you from our end to all of you for joining today. And we hope you would have an enjoyable, interesting line of talks to follow in the both days of the workshop. So have a pleasant evening. Thank you.
Thank you very much, Dr. Garni, for that most colorful introduction about all the speakers and the collaborators joining in today. I hope our participants are really excited for the rest of the workshop. So without further delay, I would really like to invite our speaker for the first session, for the second session of the day, how bionic limbs are improving lives, to understand the need of this technology. So I am honored to invite Professor Ruan Gopura, who is a professor of mechanical engineering, the director research, and also the head of department in the Department of Medical Technology in University of Moratuwa. So to introduce Professor Gopura a bit, he received his Bachelor of Science in Engineering degree and the Masters in Engineering degree from University of Moratuwa. Then he went on to receive his PhD degree in Robotics and Intelligent Systems from Saga University, Japan in 2009, where he continued to carry out postdoctoral research on biorobotics in Japan. He has expertise in developing wearable robotic devices such as robotic prostheses, orthoses, and exoskeletons. He has obtained several patents on assistive robotic systems and wearable technologies, while also having authored around 115 research articles, including multiple peer-reviewed journals and conference publications, which have gained over 1,500 citations by 2020. Presently, he is serving as an academic editor for the Applied Bionics and Biomechanics Journal and as an associate editor in the International Journal of Electrical and Computer Engineering. Besides, he serves as the guest associate editor for the special issue on EMG-EEG signal-based control of assistive and rehabilitation robotics of Frontiers in Neurobiotics Journal. He also served as the lead guest editor for the special issue titled Robotic Prosthetic Limbs in the Journal of Robotics. So it is, I consider it a great honor to hand over this session to Professor Ruan Gopura to conduct his presentation.
Thank you very much, Chaturani. So, good evening, everyone. So, first of all, I would like to take this opportunity to thank U.S. Embassy, American Center, and Makerspace Program, especially Mr. Kulutunga, who invited us to carry out this workshop. So, in the first session, I'm going to introduce you about the Bionics Limb, especially, and how these limbs can improve the quality of life of the physically weak or amputated people. So in this session, I will have a presentation which includes several videos, because to speak about the Bionics limbs as well as robotic prosthetic limbs, we need to go through some videos. So in my presentation, I have 34 slides. I'll take about 40 minutes for the presentation. So first I will discuss about a bionic device. What is a bionic device? What are the usages of this device? And then I'll move into the bionic limbs. So what is a bionic limb, and what kind of usages, and what kind of help that we can get from bionic limbs, and what are the current technologies, what are the work that we have carried out at the Bionics Laboratory, University of Moratuwa. So I'll be discussing at the end of this session. So before moving to the main content of the presentation, I'll just introduce you about the Bionics Laboratory of the University of Moratuwa. So at the bottom image, you can see the entrance of the University of Moratuwa, and then we have the Bionics Laboratory outside view, and you can see the Bionics Laboratory inside view. We have a lot of posters to educate our student, and then you can see the motion analysis laboratory that we are carrying out some experiment with the Bionics limbs. So in this session, I think we will more focus on the basic introduction of Bionics limbs, since I think in the audience we have the university students, school students, as well as different people with different knowledge about the Bionics limbs. Therefore, we will start from the basics and the fundamentals. So in this workshop, so as Dr. Gaini introduced, we have four main speeches, and we will have 2 speeches to introduce the success stories. So the beauty of this workshop is we have 4 main speakers and 2 other speakers. All the speakers are alumni of Bionics Laboratory of the University of Moratuwa, as well as all are in different countries. Dr. Tilna is in now UK, and Dr. Sanjay, who is the first student of the Bionics Laboratory, now in Japan, as well as Mr. Achinta, who is recently graduated from his MSc, now doing his PhD at USA. So with the expertise of all these people, we will have a good workshop, and we think that we can inspire young, inquiring minds through this workshop. If I little bit explain about Bionics Laboratory, you can see the top left-hand corner, Bionics Laboratory, and then the other laboratories which we are carrying out experiment and work related to Bionics Limbs. As mentioned earlier, we have motion analysis laboratory where we can do motion analysis. We have several related software and equipment related to motion analysis. In addition to that, to develop Bionics Limbs, we need support for manufacturing. For that, we have workshop facility, as well as we have die and mold facilitation center where we have high-tech machines to develop these Bionics Limbs. So some of the equipment that we have at Bionics Laboratory, as well as the CEBI Motion Laboratory, we have EMG extraction system. You will get to know about what is EMG probably later in my presentation, as well as tomorrow, Dr. Sanjay will explain about what is EMG and how we can use EMG signals for the control of Bionics Limbs. So EMG actually is a muscle activity level. From that, we can get the muscle activity, and those muscle activity can be used to control Bionics Limbs based on the human motion intention, because these limbs should be controlled based on our intention, human motion intention. We have EMG acquisition system as well as EEG acquisition system to carry out these developments. In addition to that, we have related software. I think some of you know about some of the software like SolidWorks, MATLAB. In addition to that, we want to take some other software to do work related to Bionics Limbs. So to get to know about human anatomy as well as how the systems works, we have taken the biodigital system, and we have EMG acquisition system and the software related to that, and also EEG acquisition system and software related to that. In addition to that, we have biomechanical analysis software, Anybody, and we have software related to motion analysis. In the motion analysis laboratory, we have these software. Right. So let's go into the main topic. So what is a bionics? Bionics, bionic devices, Bionics Limbs. So terms sometimes we interchangeably use. So bionic is a multidisciplinary area where several disciplines are combined together. Biology, especially mechanical engineering and electronic engineering, are combined to develop bionic devices. Of course, other engineering disciplines are also involved, but mainly biology, mechanical engineering, and electronic engineering. So these bionics can be identified as the study of mechanical systems that function like living organisms. Now, if you can see the image there, we have prosthetic devices, lower limb, upper limb, and different devices that can replace the body parts. So you can see a heart valve, ear cochlear replacement, and different other devices which sometimes replace, sometimes which enhance the organs of living beings. So in this workshop, as well as in most cases, as living being, we consider the human being. Right. So bionic devices can be categorized in several ways. So I have given a category where I have categorized it into 3 types: orthoses, prosthesis, and other device. Orthoses are the device which replace a missing body part. Prosthesis are a device which support, facilitates, strengthening, or enhance the power of the available device. The specialty is, and also the difference is, prosthetic, you don't have your natural body part. For that, you will have to use artificial body part. But for orthosis, your natural body part is there. What you will do with an orthosis is you will give the support for the available body part. In addition to that, some other devices are also available as bionic devices. So why we need bionic devices? So my topic is how bionic limbs are improving lives of amputated or a person who does not have the natural device. Now you can see in these photos, so 3 people are playing football. So they like to live their normal life. And the lady, you can see her limb is amputated above the knee. So these kind of people would like to carry out their daily activities, and they would like to live their normal lives. For that, we need some support. Now, if you consider about the current situation in the world, there are a lot of limb amputees are available. What do you mean by amputees? Replacement of the limb. Now, it is predicted that the number will double when it's come to 2050. So for these amputation, a lot of reasons are there: traumas, some diseases, accidents, as well as casualties of war. So a lot of amputees are available in the world, and we can see the number is increasing. In this situation, as scientists and as engineers, we should think different ways to support these people. At the same time, because of the aging population, what I mean as aging population, as you can see in this diagram, the age population, age over 60 years or above, is increasing. It will be doubled again 2050. So usually age people most of them are physically weak. At the same time, you can see in the second diagram, working age population has come to peak in 2010. Now it's also again reducing. So the elderly population is increasing, a working population is reducing. So therefore, in this situation, there is a requirement, and there are discussions how we cater or how we support or how we facilitate this aging population. The healthcare sector faces major challenges in providing support for these people. It also affects the socio-economic growth. So in this situation, as scientists, as engineers, as robotists, we have to think about different alternatives or different methods that we can support these people. So in this situation, bionics technology can play an important role. So that's why we need bionic devices. These devices can improve the quality of life of physically weak people as well as amputated people. So I mentioned there are So we have mainly two types of bionic devices: prosthetic device, orthotic device, and we can have other category. So under prosthetic device, main type is exoskeleton robot. Exoskeleton robot is an external structural mechanism with joints and limbs corresponding to the human joints and limbs. Now you can see this image. We have inside our body our skeletal system. So if your limb is weak, if we can support from the outside of the body by wearing external structural mechanism which has joints and limbs, we can support the weak limb. So these kind of systems we call exoskeleton robot. Those are wearable devices closely fitted to the human body and work in concert with the joints and limb. So these systems we call man-machine combined systems, because so the combination of human intelligence and machine power, we can have a device which cannot give the individual, cannot give the capabilities of, which can give more capabilities than the individual person. Like if you take a machine, they are less of intelligence, human are less of power. But machine has power, the human has intelligence. If you can combine these together to have a man-machine combination systems, so we can develop a system which can support the people. So you can see a HAL 5 which is developed in Japan, Tsukuba University, and Anthrox, which is developed by us, Bionics Laboratory, 3 years back. So these exoskeleton systems can mainly support us in few purposes: clinical rehabilitation, teleoperation of different systems, power assist, and power augmentation. You can see the video which is running now. A therapist teach the device, and then device can carry out repetitive motion. From that, therapist can easily train or rehabilitate the limbs of the patient or physically weak people, which the person who needs the rehabilitation. So now the second video you can see from the outside system inside the computer is controlling. And the third one is an exoskeleton robot developed for power assist. At the Bionics Laboratory of the University of Moratuwa. Assisting your power, which is less than the usual power, is called the power assist. Power augmentation is if you need more power in your limbs to carry out, say, heavy object. That is power augmentation. So in the military persons, they need to carry heavy backpack and heavy armors. For them, these kind of devices can be used for power augmentation. So then we will move on to the second type of bionic devices, prosthesis. Prosthetic is a device which replaces a missing body part. You can see in this image, a person is there, his arm is amputated above the elbow. So above the elbow amputation we call, you can see in the bottom image, transhumeral amputation. So if the person's arm is, the upper arm is amputated, and if you have a device, artificial device, so the person can wear it, even the appearance of the person, we can make it into normal. So the different level of amputations are available. Based on the different level of amputation, we can name the prosthetic devices. So if the amputation is from the below the elbow, such kind of amputation we call transradial. For that, we can use transradial prosthetic devices. So these amputations, I think in the next session, Mr. Pubudu will discuss in detail. So based on the level of amputation, we can categorize these prosthetic devices. And also based on the actuation type, also, we can categorize these devices. Mainly for three categories: cosmetic prosthetic devices, we call cosmesis, and body-powered prosthetic device, as well as externally powered prosthetic device, which we call the robotic prosthetic device. Those devices we can identify as Bionics Limb based on the application of biological signal to the system. The Bionic Limbs term usually used for prosthetic device, but it is also used for interchangeably for other devices like exoskeleton systems. So three categories, we'll briefly describe about three categories of prosthetic devices. Cosmetic prosthetic device. These devices just provide the missing appearance and no functionality, is a passive device, no actuation. And then body-powered prosthesis. So these body-powered prosthesis, as the name indicated, body-powered, from its power is taken from the part of the available body part. These devices can also act as a cosmetic device and can provide some functionality. So you can see the first set of images, body-powered prosthetic device, where the amputation is available at the below the elbow. Such kind of amputation we call transradial amputation. So you can see the harness and cables. So what happens is, when the person carry out the shoulder motion, so this cable length change, and in this hook there is a spring arrangement. When the cable length is changing, the hook is open. From that, the person can grab the cup. And in addition to these conventional prosthetic devices, body-powered prosthetic devices, now the 3D printed prostheses are developed. We will see a video about a body-powered prosthetic device. So you can see how the person can wear the device, and you can clearly see when the person carry out shoulder motion, the hook is opening. So I have muted the sound in this video. And then the third category, so we have discussed about cosmetic prosthetic device, body powered, and third category, externally powered prosthetic device. Usually we call as robotic prosthetic device, and usually can be identified as bionic limbs. So these devices can act as cosmetic device as well as active device. They can assist your daily motions. If it is a lower limb prosthetic device, you can assist walking, sometimes running, as well as ascending, descending stairs, likewise walking the lower limb motions. And if it is a upper limb device, upper limb daily activities can be carried out using these systems. You can see a different type of robotic prosthetic devices are available. So in this video, the Bionic arm, you can see
this key grip. This allows you to hold credit cards, bank cards, car keys, etc., etc. And now move to a point. Pretty self-explanatory. This one will allow me to type on the keyboards. We then move the thumb to this position, and we can get a tripod grip. So picking small things up. We can then change the grip.
All right, you could see that the video, the device can be controlled, but to carry out some motions, especially to carry out some gripping patterns, the person has to manually change the location of the thumb. That means there is still improvements can be done in this prosthetic device, especially in this Bionic prosthetic device. So there are other bionic limbs like Luke arm, Atom touch arm. So these devices have their own capabilities, but still we can do a lot of improvements in these devices. So Autobox, several developments are available. Bionic hand, Michelangelo hand, an limb, Tusker hand. So they have their own features. So you can see the cost as well. And then we will see how these devices can be controlled, controlling of bionic limbs. So now we have studied about bionic limbs, especially prosthetic devices, robotic prosthetic devices. So how these devices can be controlled. So prosthetic device should be controlled based on the human motion intention. Now, if you want to take some object, or if you want to do some activity, when you think about the activity, the device should carry out the activities. There should not be delays or advancing. If there is a delay, the system or the bionic limb is useless. So therefore, these devices should be controlled according to the motion intention of the persons or the human motion intention. In order to control this device based on the human motion intention, usually we use electromyography signal, EMG. EMG we can extract from the muscle surface and intermuscular EMG. I think tomorrow Dr. Sanjay will discuss those things. And also to carry out the activities of bionic limb, EEG signal can also be used. Now there are a lot of research carrying out in this area. What happens when you think about to carry out motion, your motion intention or intention to move is generated in your brain, and then the intention passes through the nerve system to the related muscles, and then in the muscles, muscle electrical activity is converted to the muscle work. From that, the limb motion is carrying out. So the muscle electrical activity, if we can extract it, we can use those activity to control bionic devices. Because muscle electrical activity and conversion of those to mechanical work, there is a delay. If between that delay, if we can do process the signal and apply to a bionic device, and between that delay, if we can carry out the motion of the bionic device, the person does not feel a delay between his intention and the motion carrying out. And in addition to biological signals, physical sensors are also used. I think Dr. Sanjay will have some example of those tomorrow. Like now, if you want to do a hand motion, bionic hand motion, sometimes you can use foot pressure sensors. From using foot pressures, you can activate the hand. So likewise, the bionic limbs, important thing is the control of these devices based on the human motion intention. So this is one example of controlling bionic limb based on EMG signal. So you can see in the stump arm here, EMG or my band is used. Using that, the EMG signal is extracted. And what are the challenges of developing these devices? So we have mainly three kind of challenges. One is a design challenge. So design challenges are posed because of the complexities of the human anatomy. So because of the complexity of the human anatomy, it's very difficult sometimes to restore the same natural motion. Especially now, you had a good example in the Bionic Limb. The person has to physically move the thumb to restore the thumb for different activities or different gripping patterns. In addition to that, controlling, there's again challenge how to control these devices, especially the identification of motion intention. So these controlling challenges, tomorrow, Dr. Tilna and Dr. Sanjay will explain. In addition to that, these devices should not be heavy, bulky. For that, we have to have different accessories, especially sensors and actuators. Conventional sensors and actuators sometimes are not suitable for these devices. So then I'll quickly move to recent research of the Bionics laboratory, especially related to Bionic Limbs. In 2016, we developed mobile 5 degrees of freedom transhumeral robotic prosthetic hand. From that hand, we can get, or we can create the given motion in the diagram, below diagram. We'll watch the video of this mobile robot. So we use EMG signal to control the device. We only use the biceps and triceps muscles. I think most of you know about biceps and triceps muscle. To change the motion, you can see the person suddenly activate the bicep and tricep muscle. So the muscle signals you can see in the bottom of this page. Right. So then the another device that we have developed 2 years back, the specialty of this one is it has the abduction adduction motion of the hand. In most hands, this motion, the abduction adduction is not available. So you can see individual finger motion, little finger. So these are still research prototypes. So in a finger, we have 3 degrees of freedom. Say for the moment, we say 3 motions. Here we call the MCP, metacarpal angel. It has 2 degrees of freedom, one for flexion extension. So the hand can carry out different grasping pattern. This is power grasping. And pinch grasping. Right. So in the Bionics laboratory, we have developed underactuated mechanism. What I mean by underactuation, if we can actuate degrees of freedom, or say different motion, say more motion from say less number of actuators, that we call the underactuation. So these prosthetic devices, underactuation is very important because if we have underactuation, we can have compact design and less space and less weight in the system, which is very important for the prosthetic devices. And also the device should support for the self-adaptation. Now in the below image, you can see now usually in our hand, based on the object that we are going to grip, our hand can adapt for the size and shape of the object. The prosthetic devices or Bionics hands should also have those capabilities. For that, we have developed different mechanisms. You can see the topmost one is our first development in 2012. We used linear actuators. And then the other one, usually we carry out motion analysis and simulation before developing the actual prototype. So this is, you can see different linkages. This is a prosthetic hand which we developed 7 years back. So we have a patent for this one, local patent, especially for the mechanism. This is just a crude prototype. So the mechanism inside the finger, cross 4-bar mechanism we used. For that, we have the Sri Lankan patent. Right. So then we will see another development, tendon-driven hand.
This is to end in fire, then we shall all burn together. Watch the flames climb high into the night, calling out, Father, oh, stand by and we will watch the flames burn on and on. Parents, we will watch the flames burn on and on the mountainside. Desolation comes upon.
So you could see that hand can adapt based on the different type of object that the hand grasps. So we have tendon-driven mechanism as shown in this image. So why I wanted to show these things to inspire the young people to carry out these developments. So this is the prototype. We named it as HiPro. You can see generation of different motions. And this is the prototype. So we developed this, I think, 4 years back. Still, you can see. So the motion is very slow. That means we have to consider about the speed. But this development is stopped. Now we are not carrying out the improvement of this hand. So you can see we have used EMG myoband. Right. So then current development. Last year, we developed another prosthetic device. We named it as iGrass prosthetic hand. The specialty of that one is it tries to mimic the motion of the palm. In your palm also you have different motions, right? We call palm arching. To this, from this device, we try to mimic the palm motions. So this kind of device we call biomimetic device. So mimic the biological creature. And for the cover of the hand, we use, I think, Ninja Flex material. Right, we'll watch the video of the prototype.
iGrasp hand is a robotic prosthetic hand developed for people with transradial amputations, which means amputations below the elbow. This prosthetic hand is developed with features such as passive isometric hold, palm arching, and thumb opposition, while maintaining a close resemblance to the human skin using flexible surface materials. iGrasp consists of 3 units: hand unit, wrist unit, and clutching unit. The under-actuated prosthetic fingers in iGrasp can achieve adaptive grasping through tendon mechanisms. The passive isometric hold is maintained using a clutch system with one-way bearings. This prosthetic hand can achieve 12 grasping patterns. It can support in performing more than 70% of day-to-day activities. Let's look at some of these grasping actions.
So with that, I have come to this summary of the first session. So in this session, we discuss about bionic limbs. What are the activities of Bionics Limb? What are the categories? Why we need to develop Bionics Limb and different type of Bionics Limbs, and how we can use Bionics Limbs to improve the quality of life of amputated people. So these limbs act as a replacement of missing body parts, and they can help to improve the quality of life of an amputee by making their life more productive to the society and making their life comfortable. And in this device, still there can be a lot of improvements, especially carrying out skillful motion like writing. For that, this device should be improved. And especially when you do writing, you need to have very good controllability of the device. Those controllability with the biosignal can also be improved. In addition to that, these devices can provide the sensory feedback, especially tactile feedback to the amputated person. There are a lot of improvements and a lot of research are going on, again, providing sensory feedback to the person using bionic limbs. So we hope that near future, we will have a very good prosthetic device, especially affordable device with 3D printing technology for the betterment of amputated people. With that, and with another video, I'm going to end my speech, but we will have Q&A session. So this video is from MIT Art Lab. The head is Professor Hui. His both lower limbs are amputated. He's carrying out a lot of research related to this area. Thank you very much. So I would like to acknowledge the research team of the Bionics Laboratory, as well as copyright holders of videos, pictures, and material. Thank you very much.
Thank you very much, Professor Gopura. So I have some questions noted down that was directed by the participants. So one question was, do you provide full scholarship for students who come from developing nations, for instance, Malawi, which is part of Africa, to be trained in bionics?
Yeah, now probably the person who is asking the question from Malawi, right? So now at the University of Moratuwa, we have different type of grant, Senate Research Committee grants. If a person or a staff member can get the grant, he can recruit a student from different countries as well. So in the Bionics Laboratory for this year, we have recruited all the students, and we want to apply for the grants in next year. So if we will receive the grant, of course, since the COVID-19 pandemic situation, as a government university of Moratuwa, we have issues of funds. But if we will receive the grant, there's no barrier whether the person is in Malawi or any other country. So we would like to get them for these positions. But the visa process, so they have to look into the visa process, but we can support.
Thank you, sir. And we have some other questions. What are the highest cost contributors in bionic devices?
Yeah, highest most probably the actuators, right? Actuators, because we can develop the structure. Now different material are used for the structures. With the 3D printing, we can develop the structure with the lowest lower cost compared to the conventional material. But the actuators, if it is a bionic device, the actuator cost would be the highest.
Yes, thank you, sir. And we have another question. How can someone with a mechanical engineering background or mechatronics background enter into this field, prosthetic exoskeleton domain? Is that possible, and where to start?
Of course, it's possible now. Living experience is myself. I did my undergraduate in the Department of Mechanical Engineering, University of Moratuwa, and then for my PhD, I did robotics and intelligent system, but my development is related to bionics. So if of course you can come to be an expert in this area, even though you have a mechanical engineering degree, because these robotic devices, the core is from the mechanical component. Without the mechanical structure, so even though you have some other the sensors, actuators, and the controlling algorithms, without the structure, so these devices cannot be developed as high-tech or sophisticated prototypes. So of course you can do the related research or development in this area, even though you have a mechanical or mechatronics engineering background.
Thank you, sir. And we have another question. Can these bionic limbs used in water, like for those who are fishermen?
Yeah, different type of developments have been carried out. In our case, we have only developed prototypes. Even though in Bionics laboratory, we have developed different devices. Still, those are in prototype level, even not ready for the market prototype. But the devices developed in other countries, few of them have the capabilities of working with the environment which has dust as well as rust as well as water.
And another question is, what are the considerations that need to be made when integrating bionic systems with human body? How does the body react to those immune system, the skin, etc.?
Yes. Now, bionic devices, I think Mr. Fugudu will discuss how the bionic devices can be combined to the human. So there are different methods the device can be worn. One method is just use a harness, and another method is osseointegration. Osseointegration means directly we will put a say steel or some kind of material device to the bone. So if you use osseointegration, so in that case, we have to think about the biocompatibility of the material with the biological environment, how the material react. So the biocompatibility is important when we select the material for the bionic devices, as well as if it is not the osseointegration, but if it is the use of a harness, in that case also we have to think about the interface. I mean interface as the between the human and the device, the attachment and interface we have to think. So we have to think about especially the material, and also since we are working with electricity, but of course in DC, we have to think about the safety aspects in these devices. Those are working as I mentioned earlier, human machine system. Human is there, the machine is there, the safety is paramount. Therefore, always designers should think about the safety of the human being first, and then the safety of the device.
Thank you very much, sir. I think I'll ask one more question, and since the time is limited, we'll move on to the next, because other questions will be answered in the upcoming sessions. So, how we join with Bionic Limbs research in Sri Lanka?
I didn't get the questions.
How do we join with Bionic Limbs research in Sri Lanka?
All right. So, yeah. Now I don't know whether the person who is asking about to research or in the development, if it is for the research purpose, in different universities. Now, in our case, this level of research is going on only in the Bionics Lab in Sri Lanka. If you want to join Bionics Lab, we welcome you. But in other universities, like I think Mr. Ranjan also knows something, some companies as well as ULS University and some other universities like Jawardhanapura, they are also carrying out mechatronics related research, right? So bionic device also a part of mechatronics, we can say biomechatronics. So different universities, they have different research programs. In University of Moratuwa, the CEBI as well as Bionics Laboratory, we are carrying out related research. So of course, you can join with us. And also you can contact different universities, ULS and Peradeniya, as well as Jawardhanapura and some other universities to carry out the related research.
Okay, thank you very much, sir. I think for other questions will be answered in the upcoming sessions, and also we'll try to answer as much as possible for the questions that we can answer through the chat.
Moving on to the next session and the last session for today, which is from need to aid, the designing process of a bionic limb, will be presented by engineer Prabhudu Ranavira. So I would like to warmly welcome Mr. Engineer Prabhudu Ranavira with a small introduction. Mr. Prabhudu Ranavira is a senior lecturer in the Department of Mechanical Engineering in University of Moratuwa and a member of the Bionics Laboratory as well. He received his Bachelor of Science and Engineering degree in Mechanical Engineering from University of Moratuwa itself. He is an Erasmus Mundus scholarship holder and obtained a Master of Science degree in Computational Mechanics from University of Swansea, UK, and École Centrale de Nantes in France in 2010. At present, he is pursuing a PhD degree in biorobotics at the University of Moratuwa. He has authored over 29 research papers and received several awards both locally and internationally. He is involved in developing wearable robotic devices for medical and industrial applications with a focus on improving human-robot interaction and reducing human effort. He is also well experienced in computer-aided design, modeling, and engineering methods and tools. So we have a very experienced and highly knowledgeable panelist joining in to present on the last session for today. Engineer Prabhudu Ranavira, over to you.
Thank you, Chatrani. Thank you very much for the nice presentation. So let me get into my presentation. Okay, am I audible enough? Is the screen visible?
Yes, Mr. Prabhudu.
Yeah. Right. Okay. Thank you very much. Once again, thank you very much for the nice introduction. I'm here to discuss about the design of bionic limbs. Now, in particular, I will discuss about the design of functional prostheses, because if you consider bionic limbs, there are the next level of functional prostheses, or you have improvement of sophistication level with Bionics limbs when it comes to regular functional prostheses. So let me get into details and I will explain to you. Like in any other design process, when it comes to the design of bionic limbs or functional prostheses, you need to understand the user's needs or the user requirements. So our target audience here is the community who have lost limbs or the community who have different limbs. Now, limb loss can be due to amputation, that is surgical removal of part of the body, or indifference due to congenital disorders. Now, there are two types of limbs. We categorize them as upper limbs and lower limbs. And let's have a look at the construction or the configuration of these biological upper limbs and lower limbs. If you consider the upper limb, it consists of the following. So the upper limb or the arm has 3 joints: the shoulder joint, elbow joint, and the wrist joint. And there are 3 main segments: the hand, the forearm, and the upper arm. The upper arm is connected to the scapula of the body via the shoulder joint. Now the scapula also provides certain amount of motion to the arm, in addition to the degrees of freedom that is provided by the shoulder, elbow, and wrist. And of course, the finger has many articulations. I will get into details in the next slide. Now, if you look at the lower limb, again, there are 3 main joints: the hip joint, the knee joint, the ankle joint, which are connected by 3 segments: the leg, shank, and foot. Once again, the leg is connected to the pelvis via the hip joint. Once more, the pelvis provides certain degrees of freedom to the movement of the leg. Now, when it comes to amputation, you will have removal of certain part of the limb when it comes to upper limb in the following manner. You have, if you have disarticulation at the shoulder, you refer to it as shoulder disarticulation. Similarly, you have elbow disarticulation and wrist disarticulation. So here, the removal of the limb has taken place at the respective joints. When it comes to the hand level or finger level removal of body part, we refer to it as either finger amputation or partial hand amputation if several fingers, say for example, up to the palm has been amputated. In the case of below elbow amputation, you refer to this as the transradial amputation, and above elbow, you refer to this as the transhumeral amputation. I hope the images given next to each of the amputation types or the distal articulation types make sense to you what the different amputation looks like. Now, the worst case scenario would be the 4-quarter amputation. In 4-quarter amputation, you have complete amputation of the arm, including the scapula and the collarbone. So here is an example of a 4-quarter amputation for you. Moving on to the lower limb amputation. Now, the lower limb amputation, once again, at the joint level, you can have disarticulation. So the hip disarticulation, the knee disarticulation, and the ankle disarticulation. Once again, at the foot, you might have removal of several fingers or several toes, including toe, as well as certain part of the foot you may remove. This is referred to as partial foot amputation, whereas below knee amputation is referred to as transtibial amputation, and above knee is referred to as the transfemoral amputation. So the images given next to each of these amputation, I hope it makes sense to you now. Now, the worst case scenario would be the pelvic amputation, which results in the removal of the entire leg. In addition to that, a part of the pelvis, which is indicated by the figure given here. Now, when it comes to the limb loss or the limb difference community, the idea would be for them to actually live the life normally, just like a normal person would. Now, for this, we need to come up with solutions. So the solution here is the prosthesis or the prosthesis. There are 3 types of prosthesis to talk about: the passive or cosmetic prosthetic, the body-powered prosthetic, and the externally powered prosthetic. Now, as Professor Gopura has mentioned, the passive or the cosmetic prosthetic provide only aesthetic appearance. They provide a limb to hide the unavailability of the lost limb. In certain instances, they also provide some structural support. Now, these are not functional. These are just for cosmetic purpose. It is just to give appearance. Whereas when it comes to functional prostheses, such as the body-powered prosthetic or the externally powered prosthetic, they provide certain level of functionality. Now, in the case of upper limb prosthetics, body-powered prosthetics. You have hands and hooks, which can be used to grasp objects, which are the hook or the hand is actuated with the use of a body powering mechanism. For this, we use a harness and a wire cord that is attached to the hook, which results in opening and closing of the hook when the shoulder is moved or when the arm is moved. I will get into details in one of my next slides. When it comes to the lower limb prosthetics, so you have here a knee joint mechanism. This is what you call a 4-bar link knee joint mechanism, which represent the lost knee joint and provide certain amount of functionality to articulate the knee during ambulation. Say, for example, walking, which is necessary because if you end up with a rigid leg, such as in the case of cosmetic prosthetic, if you have a rigid leg, then it would be difficult for you to walk because then you have a straight leg which hampers or inhibits the natural movement patterns. So with the addition of these joints, mechanical joints, it is possible to flex the leg and then have a more natural pattern to walking. So this is why they are called functional prostheses, because they provide certain amount of functionality which the biological counterpart earlier had, but they are not perfect, but they do not provide overall functionality. That is where the externally powered prosthetics comes in. So now these externally powered prosthetics, they are also known as robotic prosthetics or advanced prosthetics, but I think you better know them as bionic limbs. So what are the main differences between bionic limbs and the body-powered prosthetic? Now, definitely with bionic limbs, whether it's the upper limb or the lower limb, you will have certain type of actuator that is actually making the movements instead of relying on the body power of the wearer. Such as now, for example, here we have the loop arm, one of the well-known bionic arms, which is powered by a motor at the elbow. And then here also you have at the shoulder 2 different actuators, possibly DC electric motors that are providing 2 degrees of freedom or 2 types of motions at the shoulder. So these shoulders and elbows are powered by either electric, pneumatic, or hydraulic actuators. If that is the case, basically now you are moving towards external powering. So you have to have certain power source to power those joints, in addition to having actuators. But that's not the end of the story. Then you need to have a method to control these actuators. You can use the biological signals available in the residual limb. So after disarticulation or amputation, now you end up with a residual limb. So the residual limb will have muscles in them, and in these muscles you will have the neural system, whatever that is remaining. Now, do remember the brain signals are still being transferred across these neural system, and this is now going nowhere because now the limb is no more, or part of the limb is no more. However, these neural signals, if they can be captured, we can now talk to these actuators and tell them what they need to do. That is exactly what is achieved with bionic limbs. Now, you'd have muscle signals. We refer to them as myosignals or electromyography signals. You also have brain signal or electroencephalography signal. So this is what we refer to them. And when it comes to the lower limb externally powered prosthetics, the idea remains the same. We rely on actuators, we rely on external power sources, and we rely on myoelectric sensing methods or myoelectric signals or brain signals, or it can be physical signals that is coming from the sensors attached to the device itself. So thereby we achieve the control that is required to, at the end of the day, to achieve these natural motions which is desired by the amputee. That's the idea here. Overall, so if I tell you, the prosthetic limbs are artificial devices that substitute or replaces missing body part or limb. There are different types of prosthetic limbs. You have the transhumeral prosthesis, transtibial, radial prosthesis, the hand prosthesis, the partial hand prosthesis for the case of finger amputation, and you have finger prosthesis when it comes to upper limb. When it comes to lower limb, you have hip prosthesis, where you have pelvic amputation, and then transfemoral prosthesis, transtibial prosthesis, foot prosthesis, and partial foot prosthesis. So now all of these devices, to a certain extent, substitute or replace a missing body part only. So now, so what's the difference between bionic limb? If I express that again, it's the next level of sophistication of functional prosthesis or the regular prosthetic limb. So a bionic limb is a sophisticated artificial device that tries to restore the normal functions of the missing body part. It can be the upper limb or the lower limb or parts of the upper limb or lower limb. So here are some examples of the bionic arms, the bionic hands that is available commercially. You can, in fact, except for the Luke arm, you will be able to, in fact, if you have the money to spend, can purchase these devices and use them. However, as you can see, they are not available at a cheaper price. So that's why we need to invest more people. We have to have more people coming in doing researches in these areas, so we can bring these costs down, so the regular people with regular income can have access to this technology. So that is one of the reasons why we are having this type of works. So if I just go through the different types of bionic legs, what you find here, these are there are very well-known commercial manufacturers that are responsible in developing the bionic legs. In fact, all the images what you see here, they are commercial products, except for one or two, which are being conducted at universities, the researchers which are output of researchers conducted at certain universities. So the next up, let's get into the design considerations. Because now you are listening to my talk because you yourself is interested in designing a bionic limb, or I would say rather say functional prosthesis, because I wouldn't want you to touch the sky immediately, just start to walk, then run, then jump. So I will go through that ideology, because I've seen there are many comments. So you are into this technology. So let's start from the letter A and then work ourselves towards letter Z. So now when it comes to design considerations, now they are the aspects that influence derivation of effective solutions for the amputees. Now, so what are the design considerations that are very important for the development of functional prosthesis? So here I have a few. Now I will go through each of these in my presentation. So to a certain extent, the time permits. Now here I have mentioned the function. It is important that first we understand the function of our prosthesis, or depending on the level of amputation or the limb loss or the limb difference, we need to consider what functions are missing. Accordingly, we need to plan for the device, because the device that we are going to come up with is a electromechanical or of that nature, which will have its own limitations because of the limited limitations of the technology, the complementing technology. So we need to be very conscious about what functions we are going to support with this prosthesis. You also need to be aware of the human body sizes and shapes. So this area of study is what we call anthropometry. You also need to be aware of the anatomy, what is under the skin. Now there are cells that makes up the human body. So there are subsystems that makes up the human body. For example, the skeletal system, the muscular system, the nervous system. You have also connective tissues, and so on and so forth. There are different types of subsystems that makes up the human body. So you need to be knowledgeable of these human subsystems, because at the end of the day, you are going to replicate their functions. So you need to have a proper understanding of the anatomy. And then you need to go into the details of the biomechanical measures. Now, what are the biomechanical measures I'm talking about? The kinematics, the kinetics. Now, what are kinematics? When it comes to a given limb, say for example, upper limb, the elbow. So the elbow moves when it does a certain function, the elbow moves, and about the elbow, the forearm rotates. So if you consider the upper arm as the reference and then forearm as the segment which moves with respect to the upper arm, the forearm is moving with respect to the upper arm. So now you have angular rotation of the forearm. So here, angular position, you need to calculate, or you need to understand, determine. Similarly, you need to understand the angular velocity, angular acceleration. So these are the main parameters that needs to be realized under kinematics, because you need to tell the robot, the bionic limb, how to move, because you are using actuators to move them in manner in which how they need to be moved. You need to tell them, and then this movement has to take place, right? So that has to be first recognized and then understood. So the kinematics involves the forces and moments involved in making these movements. The forces and moments involved in making these movements. So you have joint reaction forces taking place, ground reaction forces taking place when the body is interacting with a third-party body. Say, for example, the foot is standing on a ground. So there is ground reaction force being acted on the foot. So how it varies as the body moves over the ground when you walk. So you need to understand accordingly the forces exerted on the prosthesis can be calculated and known, and a proper decision can be taken with regard to the structural performance of the system. So that is why you need to do. And then ergonomics. Now there are two aspects to this. There is the physiological ergonomical aspects, then psychological ergonomical aspects. In particular, when it comes to physiological aspects, so you have to understand that now here bionic limb or functional prosthesis is a device that we wear on our body. So there is always that interface between the device and the human. So across this interface, communication takes place. The human has to explain to the device what the device needs to do. Now this communication takes place through this interface. And then the device, whatever the device feels, or haptic feedback, sensory feedback, will be sent across to the human through this interface. Now, knowing how to design this interface is very important. And here, do remember, not only that, this communication, but also the forces, whatever the forces that are exerted will be exerted through this interface. The reaction forces that are felt by the device will also be transferred to the human through this. So all of this you need to consider when it comes to properly designing the system to make sure it is convenient, it does not create discomfort that reduces the user acceptance of the amputee when using these systems. So it's important that the system is able to quickly respond to the human, at the same time do it in a convenient and a comfortable way. So likewise, now I have spoken about the biological and biomechanical aspects under design consideration. Similarly, now you have the technological aspects to look into. Now, when you are designing the prosthesis, especially when you are working out the mechanical design, you need to have some knowledge when it comes to technology, that is mechanical systems, power transmission methods, mechanisms. So you need to have some background understanding of the technology which you can use for the purpose of developing this prosthesis. And then what are the control methods available, control strategies that you can use, what sensors and actuators can be put into the design to provide the functionality that was understood, that was identified initially, and the different power sources that are available. Now you have tethered power sources, you have portable power sources. For example, the battery packs, and what are the different types of batteries which can be adapted in the design. So these things you need to be aware to make a proper selection. And of course, at the end of the day, after the design process, you need to convert this into a tangible product. So you need to have a proper understanding of the materials which you can use, the different manufacturing methods that can be applied, and essentially the tools that are there to perform the design as well as the fabrication of the prosthesis. Now, when I talk about tools, not just the hardware, but also the software, there are different tools which can be effectively used to the design process. So this is exactly the focus of our discussion. Now, going through the function, now, as a human being, there are certain everyday activities that we do. Irrespective whether it's the amputee or the normal person, each person wants to have same type of living. So same type of work needs to be carried out, same type of requirements might exist. So we need to have that empathy within ourselves to understand, okay, what the device should do for them, for the needy. So there are 3 types of activities that I've identified as per the paper published given in the source. So here are those 3, the domestic activities of daily living. Under that, you have food preparation, housekeeping, laundry, telephone, and computer use, office tasks such as writing, hobby or sports. So these are regular domestic activities we need to perform. In addition to that, you have extra domestic activities such as transportation, driving, shopping, employment-related tasks, trade-related tasks. And finally, you have physical self-maintenance, such as feeding, medicating, toileting, bathing, dressing, grooming, ambulation. So these are the typical activities which the processor should provide for. Now, going into the measurements of the human body. Now, in order for us to design the prosthesis, we need to have a proper idea of the measures of the human body, such as size and shape. Now, there is a specific science behind this, the area of anthropometry, which describes the systematic methods for measurement of physical properties of the human body. Now, there are anthropometric charts which you can refer to. Now, I have extracted 2 charts coming from this particular source, the measure of man and woman, human factors in design, that explains the length or the sizes of the body segments as per the percentile population. Now, the 5th percentile, 50th percentile, 95th percentile, likewise, there is a way how we describe the sizing of the body to generalize the body proportions. So we need to have some understanding of these sciences and the theories. And then you could also go into perform the anthropometric measuring with the use of tools. There are specialized measuring tapes, anthropometers, spreading calipers, sliding compass, head spanners, like so on and so forth. Many different types of tools available for performing the size measurement. However, when it comes to performing shape measurements, there were limitations in the past, but no more. We have now 3D construction methods available for us. The 2 main 3D reconstruction tools that we can use nowadays are 3D scanning and MRI CT scanning. When it comes to 3D scanning, now you have 2 mainly different, two commonly used 3D scanning technologies: the structured light scanners, the laser scanners. Now, with these scanners, we are able to produce a 3D point cloud, and using that, now we are able to go through our design process. A much more expensive method would be MRI CT scan. MRI stands for magnetic resonance imaging. CT, computerized tomography. Now here, even soft tissues, we are able to actually get a 3D scan or 3D reconstruction of the bones. The muscles can be done. However, there are inherent limitations. As you can see, when you lay on the bed, the muscle gets deformed. So there is a concern of using this technology for the purpose of designing prosthetic sockets. Perhaps that could be an area that needs to be looked into. Now, the most exciting technology, as a technologist or as an engineer, it could be the 3D scanning technology. Now, there are very expensive 3D scanners, such as the Faro one. that cost more than $100,000 perhaps. But there are much more cheaper versions which provide less precision. Now, less precision is not necessarily bad, but there are limitations. That is something you need to be aware of. So here I have given a few examples, but these are some of the examples that I have selected for this discussion, but not limited to. Now, when it comes to anatomy, there are 4 different systems that you need to be quite knowledgeable of. The skeletal system, the connective tissues, the nervous system, the muscular system. Now, the skeletal system is the system that provides structural strength to the human body. Now, when it comes to the connective tissues, now the bones do not stick themselves just like that. So basically, the bone to bone, there is no connection. You can't stick bone to bone just like that. So in order for the bones to work together, you have to have connecting tissues. Now, these are mainly ligaments, but in between the bones, you also have cartilage that reduces the friction between the bony segments. And then in addition to that, you have tendons, and then you have the muscular structure. So likewise, the biology you need to also understand. And when it comes to biomimicry, if you are trying to develop a biomimicking prosthesis, so all of these structures, the skeletal system, the connective tissues, the muscular system, all of this, you need to be able to reproduce to a certain extent to provide those functionality. And then you have the nervous system that provides the electrical signal to the individual muscles. Muscles are essentially the actuators of our body. So it's the neural system or the nervous system that provides the information what to do from the brain or from the central nervous system. Now, I would like to actually switch to something interesting. I know these talks can be somewhat dull. So I have something to show you here, because at the end of the day, I suppose you would want to try things out for yourself, isn't it? So I hope this is visible to you. Now, what I have here is biodigital human application. Now, biodigital human application is freely accessible for you. If you search in the search engine, you should be able to find, if you type biodigital, and by loading the human anatomy onto your screen, you should be able to actually now navigate this and then understand how the body is composed of. System by system, it shows how the body is composed of. Now, say for example, if I want to hide the muscular system, here I have an option to hide the muscular system, and then have a look at what is underneath the muscular system or in between the muscular system. You can further go on to hide the nervous system, and then even you have the option of turning off the connective tissues. And here you can clearly see now what the human body consists of in terms of the skeletal system. So here you have the collarbone. So if you select the part, the collarbone or the left clavicle bone, and if you select the humerus bone, you can see the left humerus bone, and this is what you call the scapula. So the left scapula. Likewise, you should be able to go through each and every segment and then understand the construction, even the finger, detailing the each and every bony part, the phalanges, the metacarpal joint, the body parts, all of it, one by one, you should be able to understand. So likewise, so this is an exercise which you can try out later on at the end of the presentation. Okay, so then you can continue to add different subsystems. So if you open connective tissues tray, you have two types of connective tissues. You have axial connective tissues and pendicular connective tissues. So if you turn on the only the axial connective tissues. You can see what are the actual connecting tissues that are there inside the human body. But if you want to see the appendicular connective tissues in particular, which is of interest to us, you turn on the filter to visualize the appendicular connective tissues. If you select these segments one by one, you will be able to identify its name, how and where it is inserted onto the bone, which keeps this joint complex together. So that's the idea. So let me switch back to the presentation. Now, you also need to understand the degrees of freedom and the ranges of motion of the upper limb. Now, you have shoulder joint, you have the elbow joint, and the wrist joint. So at the shoulder joint, you have 3 degrees of freedom. Now, they are referred to as abduction, adduction, and the ranges are shown on the slide here. And then the flexion, extension, which is shown here in this image. And then you have the internal, external rotation. So here, the arm is, when the arm is moved towards the body, that is internal rotation. When it is moved outward, you have external rotation. Likewise, you have abduction, adduction. Adduction means moving away from the body. Adduction means moving towards the body. So these are the 3 degrees of freedom. At the glenohumeral joint, you have. But in addition to that, I said you have scapular motion taking place. Now you have sternoclavicle joint here. Sternoclavicle joint here, about which 2 different types of motions are possible. Elevation and depression, as shown here. Protraction and retraction, as shown here. So this is, in fact, protraction and retraction motion that is specifically used in body-powered upper limb prosthesis. So the elbow, so if the forearm is moved towards the upper arm, so that's what you refer to as flexion. And if you move away, that's extension. So supination and pronation. So while holding the hand in a neutral position, such as shown there, and if you move, rotate it towards the rightward side, such that the palm faces upward, that's what you call supination. And then the other direction is pronation. And when it comes to the wrist, so if you move the wrist towards the leftmost direction, that's what you call radial deviation, and towards the rightmost direction, ulnar deviation. So you have radial ulnar deviation possible. So you can actually try this out, right? While you're listening, these motions, whether it's possible for you to make them, you can try them out. And then when it comes to the wrist, so the flexion extension motion at the wrist, flexion means you move down the palm in the downward direction. You move the hand in the downward direction. So this is flexion for you at the wrist. And then if you move it up, you have extension. So these types of motions and the ranges of motion, you need to be able to reproduce, or to a certain extent, to a certain limit, you need to be able to reproduce with your prosthesis. The hand is a complicated biological entity. In fact, the hand has 27 degrees of freedom. There are 4 degrees of freedom per finger, 5 degrees of freedom per thumb. The thumb here, so you have 2 thumbs for the 2 hands, and then you have 6 degrees of freedom at the wrist. Here you have 6 degrees of freedom, including the 2 degrees of freedom, radial ulnar deviation and the flexion extension. Okay, so in addition to those 2, there are 4 other degrees of freedom. Do you notice the fact that there is a bunch of bones here that provides this higher degree of mobility for the hand? Usually, now all of these are held together with the use of the ligaments, which I mentioned, which I've shown you in the biodigital anatomy module. Now, if you actually have a look at these joint structures, so you have the little finger here. So the little finger and the rest of the fingers, if you consider, they have the same construction or biological construction. So you have, this is where you have one of the joints. It is called the distal interphalangeal joint. This is proximal interphalangeal joint, whereas this is metacarpophalangeal joint. So at these 2, distal and proximal, you have 1 degree of freedom, whereas at the metacarpophalangeal joint, you have 2 degrees of freedom, which provides the ability not only to flex, extend, but also abduct, adduct. And then you have, for the thumb, again, interphalangeal joint, 1 degree of freedom, the metacarpophalangeal joint 1 degree of freedom, but in addition to that, at the trapezial metacarpal joint, you have 3 degrees of freedom. So you can see that is why the thumb can do a lot of work. It can move into different positions. I'm sure you listened to Professor Gopura's presentation that in some of the bionic devices, they do not provide all these movements because it is difficult, because to achieve each of these degrees of freedom or movements, you need to have a specific actuator that drives these the movements. For example, now here you have abduction, adduction movement of the fingers, and then flexion, extension of the fingers. And when it comes to the thumb, basically you have reposition, opposition movement, and then you have abduction, adduction in the radial direction. In the palmar direction, you have abduction, adduction. Likewise, flexion, extension here. There are many different types of movements which can you achieve. So the hand is a complex biological entity to model and reproduce. When it comes to use of the upper limb, think about it for yourself. How do you actually react when it comes to using the upper limb? There are 3 different steps that we normally go through. So those are reaching, prehension, manipulation. So what is reaching? Reaching is reach the object or position in space, avoiding obstacles. So if there's an obstacle, we know how to move our hand, avoiding the obstacle. And then prehension means while we are actually reaching for the object, we will now configure our fingers in such a way so that we can easily and quickly grasp the object. It depends on the type of object you are going to grasp, whether it's a key, pen, cup of water, bottle, computer mouse, button on the keyboard. Accordingly, we will change our finger patterns. So this happens naturally. So this is what you call natural motion. And finally, manipulation. So when you have taken the object in your hand, manipulation refers to ability to adjust and position objects in hand, right? So it depends on the type of work that you do. It can be a simple push-off button, which only requires the manipulation of just pushing the button, whereas you might end up with holding a bottle or a cup of water and then moving the bottle or the cup of water in your hand into different orientations. So now, this is quite a broad topic to discuss about. There are many different grasping patterns to speak of. So we here, in order to simplify things, I will just classify the different grasping patterns into 2 classes. So the grasping, now this I will do so as per the Kapkowski grasping taxonomy. But notice the fact that there are different types of grasping taxonomies that have been presented in literature, such as the modified Fick's grasp taxonomy. But if you consider the Kapkowski grasping taxonomy, so you have basically precision grasp patterns and then power grasp patterns. And when it comes to grasping, we can identify most objects that are to be grasped are either circular in shape or prismatic in shape. So if it is prismatic in shape, so we are more prone, if it is a precision grasp, right? You would need to be carefully taking up the object. Say, for example, use of a pen or pencil or threading a needle. So that is where we get into a precision grip. And then, of course, you would also work with circular grasping patterns to work with circular objects. And then when it comes to power grips, most of the time, it involves wrapping of the fingers around the object. It could be circular, it could be prismatic. In the case of circular, say you have spherical board, which you would tightly grab with all the fingers, also using part of the palm to support the lift process. So likewise, the finger orientation, the manner in which how the fingers is manipulated before the grasping takes place. So the grasping taxonomy basically explains the different varieties that are there. So if you plan to do a design with regard to hand design, this is the place you need to visit first. You need to first understand the different grasping patterns and taxonomies that it explains. Let's get into the mechanical design aspects of design of upper limb body powered prosthesis. Now, if you take the 2 prostheses that are given on the slide, you have transradial prostheses and then the transhumeral prostheses. So the usual configuration include the terminal device, such as a hook or a hand. You have a wrist unit, which you can actually use to change the position of the terminal device. Then you have the socket, whether it's transhumeral, you have arm socket. If it is transradial, you have forearm socket or forearm shell. And then you have a harness. And connected to the harness, you have a control cable that is attached to the hook or the hand. Now, how does the hook operate? Now, it is quite straightforward. Let me try to simplify things for you. Now, you'd notice here, the person here, the amputee, a transradial amputee, is wearing the harness. So now here, the hook is normally in a closed position. Now, how is that possible? With the use of elastic bands or springs. Now, if you put a spring or an elastic band in such a way so that the hook stay closed. So that's what you call always closed, right? So this is a closed configuration, right? Now, with the control cable attached to the harness, now the harness is positioned in such a way so that when you move the scapula in such a way so that you protract or retract, the control cable gets pulled or relaxed. In the case of protraction, the control cable gets pulled, so which makes the hook to come apart, overcoming the forces exerted by the elastic band. So you need to overcome the force of the elastic band. So you notice here that now the wearer is required to apply a high enough force to separate the pins of the hook. So likewise, there are limitations to which the gripping force can be modulated or controlled with this body-powered prosthetic. So now, if you move on to the externally powered robotic prosthesis. Here, I have 3 examples: shoulder bionic limb, the transhumeral bionic limb, and the transradial bionic limb. Now, each of which are inserted with or included with actuators, and they are controlled by myoelectric signals. Now, this is the famous loop arm. So at the shoulder unit, you have actuators to support as many degrees of freedom. So with loop arm, you have 2 degrees of freedom support. And when it comes to the elbow unit, you have a separate actuator to provide the flexion extension capability. Again, here, the control signals come from myoelectric means. And then you have the wrist unit. The wrist unit may have degrees of freedom inbuilt into the design or may not. It might depend, because putting up many actuators, as many as you can see here, now you have fingers, you have thumb, now you have wrist. If you are planning to support all these degrees of freedom, all types of motions, then you have to have a certain place to put the actuators. Then there, and you notice here, this has to be low in profile. You cannot have a large size forearm, because it looks out of proportion. It could well be heavy. I mean, it could be too heavy for the user to handle such a device. So then there are compromises always, right? So if the technology, as and when the technology improves, or who does improvement to this technology, it might be you at some point of time. Yes, you can miniaturize. And then you have a transradial bionic limbs. So basically, you only have to worry about the finger actuation and then the wrist actuation. This is how the externally powered robotic prosthetic or the bionic limbs are designed. Irrespective whether it's the bionic limb or the functional prosthesis, you need to work on the finger mechanism. So this is where some level of innovation can come in. I'm sure you were listening to Professor Gopura's presentation. There are certain developments at the Bionics Lab at University of Moratuwa were presented. So let me explain a bit about the design process when it comes to developing finger mechanisms with the limited time. So here there are several aspects that we need to achieve. You need to achieve natural motion. That is for sure, because now what is natural motion? When it comes to the hand, as you can see, now the phalanges tend to move in a synchronized manner. It's not that one phalange moves and then the next phalange moves later on. It doesn't happen one after the other. Everything happens simultaneously. So they have to be very well synchronized. So the same has to happen when it comes to the bionic hand or the functional hand. So the individual phalanges don't move by themselves, but they move in a synchronized manner. So this you need to be able to replicate. And then shape adaptive. So when we wrap our finger or the hand or the fingers about an object, you notice that when an object comes into contact with one of the phalanges, that phalange stops moving, and then the other phalange starts to move. So as like what is seen here. So you can see here, this is what we call the one of the phalanges here. Okay. So here it is referred to as the proximal phalange. It is proximal to the joint of the say it is proximal to the palm. So here we call it the proximal phalange. So as the phalange moves, when it comes in contact with the object, the finger stops, that particular phalange stops moving, but the rest of the phalanges, the distal phalanges, starts to move and hug over the object, and it wraps around. So this is what you call shape adaptivity. No matter what the shape is, the fingers should be able to wrap around the objects and grasp. So the self-adaptiveness property is a requirement, a prerequisite when it comes to finger mechanism design. And then the grasp force application. Now, it could be a static load that you are supplying. It could be a dynamic load. Imagine that you're holding a cup of water or a bottle. So you're filling up water inside the bottle. So now the force that is exerted on the hand changes. And then you might have slipping taking place. So then the grasping force has to be gradually increased. Not to an extent where you crush the bottle, but to an extent to keep the bottle from slipping. So this is what you call force isotropy. Force isotropy. And then it has to be durable. It should withstand regular day-to-day use. So the weathering effect, whether there was a question about the ability of the prosthesis to withstand environmental conditions in what manner. So that we actually recognize this. So there are standards for this. For example, now the waterproof and dustproof, it is given by a particular standard called IP67. So likewise, there are different standards that designers might need to meet to design the prosthesis. So then the compactness, it has to be smaller in size. It has to be comparable to the human finger to the best possible extent. It has to be less in weight. Now, know for a fact that now the human hand has certain weight. It is about 0.6 kilograms. Now, the hand that you develop should also be around that particular weight. And then when it comes to fingers, I said there are many degrees of freedom. There are many degrees of freedom. So each of the degrees of freedom, you have to be able to support. However, it is not possible if you want to have a compact system, putting up many actuators in the hand or somewhere in the area of the wrist may not be possible. So then we have to find methods to reduce the number of actuators, but still get that natural motion, the shape adaptivity, the isotropic grasp ability. For this, there are under-actuation mechanisms that have been developed. So there are tendon-driven mechanisms, there are linkage-driven mechanisms. So you have tendon-driven mechanisms, where you have a tendon running through the phalanges, and then you have spring supports. So when the tendon is not tensed, so the phalanges stay straight. And when the tendons are when the tendon is basically tense, then the phalanges will flex. And then you have the linkage driven mechanism. Again, here you have one point of action where the actuator push on the link, which causes a 4-bar link system to flex and adapt onto the object. Now here I have some examples of finger actuation method. Okay, I'm sorry. Let me play the video from the beginning. Okay, let's have a look. So now here, linkage-driven finger mechanism. Now here you have a stackable 4-bar linkage. So there are several 4-bar linkages that are stacked over one another, and a contractible slider crank mechanism to provide this so-called natural motion, the self-adaptive motion. So you can see when the distal phalange comes to a stop, how the rest of the phalanges respond. So this is the type of the mechanism that has been proposed in this particular research work, given by the title Actuated Finger Mechanism Using Contractible Slider Cranks and Stackable 4-Bar Linkage. So these are the types of developments that later turns into commercializable products. So each of the movements for different conditions are being investigated in this video. Moving on. Now here I have another video that explains the tendon-driven finger mechanism. This is far more sophisticated than the previous one, given the fact that all fingers are working. The number of degrees of freedom is 15, and have a look at the nimbleness, the dexterity within which how each of the fingers respond. Now, when it comes to durability, it should withstand a certain level of abuse. Especially, it is meant for the usage of extra domestic activities, such as trade-related activities. So these are some of the experiments that were done, of course, qualitative experiments that were done. There are much more standard approaches for doing this. This is just for the purpose of showcasing how it is durable, how strong the hands are to perform this motion. So with that, I will move on. And then when it comes to attachment methods of upper limbs, there are body harnesses that you can use. There are sockets, and nowadays there is the socketless socket designs available. Once again, the socketless socket design provides improvement to the user comfort and then reduced weight. And then this question was raised in the previous presentation, osseointegration. Now, what are the methods that are available, the advanced methods that are available for the purpose of attaching the prosthesis onto the human? The osseointegration is the most advanced method that is available. And here we use a specific material known as alloplastic material to construct this anchor, and we insert the anchor into the bone, inside the bone. Now, inside the bone, you have osseo tissues, and this alloplastic material integrates with the osseo tissue naturally, and then the bone develops around it, and then it hugs it strongly, which makes it ideal for this type of application. So the end point of the anchor is then used to mount the prosthesis. Now, during the surgery, you may also reconsider putting intramuscular electrodes to acquire the electromyography signals or the myo control that can also be achieved. Or else you can use surface electrode muscles, surface electrodes on the muscles for acquiring the muscle activity or the electrical activity inside the muscles. So these are the two options that are available for obtaining the myoelectric control. As such, so you have physical human-robot interaction, where you use physical sensors, But when it comes to bionic limbs, we mainly rely on cognitive human-robot interaction, where we rely on cognitive sensors, such as the muscle signals and the brain signals. So we refer to them as electromyography signals and electroencephalography signals. So the process of control when it comes to EMG and the process of control when it comes to EEG will be discussed tomorrow under the titles, the separate titles given in the workshop. So I will leave it there. So you may join the workshop tomorrow and then listen to the talk there, where you will learn how these EMG and EEG methods are effectively being used with the use of other technologies like AI, machine learning methods, and then other types of methods other than that, how they have been used for the purpose of control of bionic limbs. And let's have a look at the different tools that are there for assisting the design process. And of course, nowadays, computer-aided design is a necessary tool for designing any type of system or any type of product. When it comes to the processes, there is no difference. So what are the technologies available to get this done? So there are well-known 3D modeling platforms, such as the Siemens NX, Siemens Solid Edge, the Dassault Systems CATIA, the Dassault Systems SolidWorks, PTC Creo, the Autodesk Fusion 360, Autodesk Inventor, and then you have the FreeCAD. These are all parametric modeling software. These are not just 3D modeling software. These are specific engineering type of software which you can use for the purpose of development of prostheses and other bionic limbs. Now, when it comes to Solid Edge or Siemens or Creo, Fusion 360, you can definitely get student version for free. The complete functionality is provided for your benefit actually by these developers, right? SolidWorks does not provide such free licenses, unfortunately. However, the FreeCAD is an open source parametric modeling platform. So there you go. You are not limited. You are not limited. So with that, now you can see here, there are different places which you can borrow the 3D design models, the 3D scans. In fact, the places where you can borrow these CAD models as a startup is the GrabCAD, and then 3D scans and 3D printable models. You can also go to Makerbot ThingsWorks, and then you, other places such as the 3D parts database. You can find many different applications. So here, I will move on to the next slide, where 3D printing is considered as a manufacturing method. Now, 3D printing, there are many different methods which you can adapt. The adaptive processes, the solidifying processes. You have fusion deposition modeling option available. You have multi-jet modeling option available, which runs at a higher cost in comparison to fusion deposition modeling. And then you have laser sintering methods, selective laser melting methods, stereolithography methods. So some of the hobby type machinery you can see here at a much more lesser cost, whereas the high-end industrial scale ones are much more expensive. So this is an area which you should consider for the purpose of developing prostheses in future. It will be the case.
What it was like before having this hand, like having like.
Now here, I would like to show you.
Before.
Here, I would like to show you a video of a little boy whose life has been changed as a result of these 3D printed prosthetics. So let's listen to him.
Having this hand, like having like any hand, it was pretty hard. I get bullied a lot, and like I really wanted to be part of a team. I wanted to have friends. I wanted to act like I actually had like a right hand, and it wouldn't really care if I had that.
Enable is an online global community of volunteers who are using 3D printers and 3D design software to make prosthetics for children and adults who are missing fingers, hands, and wrists, and we're giving them away for free.
One of the reasons 3D printing is so well suited to this problem is no two cases are exactly the same. Some kids are missing all of their fingers, some are missing even the palm and the wrist. One of the reasons we can produce these devices for kind of incredibly low cost, well under $100, is these devices are entirely body-driven, purely mechanical, so there are no motors, there are no sensors, there are no heavy batteries. So it's a very lightweight, very simple device.
These hands don't even pretend to look like normal hands. They're very different. These things look like something Iron Man or a superhero would have, and the kids love them for that reason.
Once I had this hand, my friends would ask, "Hey, dude, how's it going? Has anything changed with it? Is it working better?" And it's pretty cool how they're actually involved. They're actually talking to me about it, and I love this because I could pick up stuff and I could help.
It's been really great to have Kieran and his family come to Pure 9, prototype these new ideas, to test drive these new hands, and to be able to see the higher perspective, what this is all about, to see how that hour of CAD, translated into him being able to hold his coat or zip a zipper better. What Enable has done is it seems that they've kind of proven that regular people can design amazing things if they're given access to the tools.
I think it's pretty cool that I'm one of the people actually testing this out for a bunch of other people. It's going to be really awesome to see it when it's so big. Every kid that has a problem like me will have a hand.
Right. Okay. I will move on. Now here, you can even find this particular website. There is a community called Enable that provides the design of these prosthetics. Now this is a hand prosthetic. Now let me go to the particular website for you. Here you will find the link, download link for the prosthetic design. So this particular prosthetic, you can even design and by yourself, or you can download and then use your own 3D modeling platform to modify, to improve, and then visualize. And then you could do 3D printing of these parts. Now here I'm using Simplify 3D, a 3D printing slicer software, to prepare the 3D prints of these parts. Now this particular software package shows the build time, 2 hours and 40 minutes, and then it also showcases how and in what manner the 3D print takes place. Now the 3D printer that I'm using here is Anycubic Mega S, and then within this particular 8-inch tray, I can print many parts as I want, not just one, as many parts as I want. So likewise, this process, now this 3D printing software also you can find for free. If you go to MakerBot website, MakerBot print slicer software is available for free. So now I would encourage you to actually go through these websites and find these models and learn the content and try to do your own bit on it as a start. So let me actually quickly go through the rest of the slides. Here, when it comes to lower limb prosthesis, again, you need to be concerned about each of the systems of the human body, how they operate. And then you need to be concerned of the lower limb degrees of freedom, the ranges of motion. Now at the hip, you have 3 degrees of freedom, the flexion, extension, abduction, adduction, internal rotation, external rotation. Then the knee has the flexion, extension, internal rotation, external rotation, motion, support to a certain extent when the knee is flexed to a 90-degree angle. If not, this rotation is not available. So essentially it's a 1 degree of freedom system. And then you have the ankle, which supports minimum 2 degrees of freedom. So flexion extension or the dorsiflexion plantarflexion is supported about the talocrural joint. And here you have another sub-level joint, which is called the subtalar joint, that supports inversion, eversion, motion. So altogether, at least 7 degrees of freedom are supported by the lower limb. So when it comes to prosthesis design, So these types of considerations have to be put into place. So when it comes to lower limbs, it is mainly to support certain type of gait. Usually the walking gait. There are other types of gait. There is the running gait, jumping gait, the sit to stand, the squatting, likewise walking upstairs, walking downstairs. Likewise, we can think of many types of gait. But when it comes to humans, the prime requirement would be walking. So the prosthesis would need to support the walking process. So here explains the walking process for a given limb, say the right limb. So through the walking process, the limb stays in a stance phase for a 60% of the cycle, and it goes through a sink phase for a 40% of the cycle. So through this particular cycle, the limb will exert forces on the ground. There will be joint reaction forces that are taking place, and then the limb will basically rotate about each and every joint. So the kinematics and the kinetics, so that is the position, velocity, angular rotation of each and every joint, and then the kinetics, the joint moment, the joint reaction forces, the ground reaction forces throughout the gait cycle needs to be understood in detail. So that enables us for the calculation of the prosthetic design parameters. When it comes to body-powered prosthetics, so you have transtibial prosthesis and transfemoral prosthesis. The transtibial prosthesis is composed of a foot unit, ankle unit, a pylon that connects a socket, and then you have pyramidal socket adapters that are used to connect the pylon with the socket. And then you have energy storage and return foot designs available. There are passive and modulated passive designs available. When it comes to the knee joint, now you have different types of knee joint to support the intricate motions of the knee. Now, typically the knee does not rotate about, the biological knee does not rotate about a fixed joint axis of rotation. There is no fixed axis of rotation. So the axis of rotation tend to migrate as the knee flexes. So in order to provide the support of this migration of the knee rotation axis, a 4-bar linkage system has been adapted by most prosthetic lower limb prosthetics. You also have a different adaptation of the same technology in order to provide certain amount of damping during stance phase to provide that balance control. You have spring control, pneumatic control, and hydraulic control damping methods available. When it comes to externally powered prostheses, you have below knee bionic limbs, above knee bionic limbs, and then you have different types of actuators in the ankle as well as the knee to provide the required motion that is essentially driven by the myoelectric sensors that are mounted on. And then you have various types of commercial level ankle joint bionic limbs available. One of the famous one is Biomedical. And then some of the other commercial available ones are also a Proprio Foot, the Autobox Empower. Now these all have motorized ankles that provides toe clearance as well as toe power. And then they provide greater degree of stability and adapt to terrain much more naturally. And as a result, reduces the metabolic energy consumption. So these other Freedom Kinetics, Ellen and Meridian, they provide certain amount of damping effect, which are processor control damping effects using hydraulic mechanisms. When it comes to bionic knees, you have Osua bionic knee, the Autobox. Now, in comparison to Autobox and Osua has a certain electric motor within it to provide the support for knee flexion. Now, Autobox only provides a certain amount of the hydraulic support, which is microprocessor control, hydraulic damping effect, just like the Osua Rio knee. Here, Osua Rio knee has a rheological magnetic fluid that provides the damping effect. On the other hand, if you take the Michigan uni, open source leg has joints at the knee and the ankle as well. So they provide much more higher degree of control. So I will in fact skip the video because of the time. The attachment methods are the following. For the lower limb, you have the socket type attachment methods. You have the osseointegration attachment methods. And then you have socket fabrication methods such as the molding process, the regular socket making process, and then making a peg and then Polypropylene sheets have been heated and laid over for the purpose of molding. But nowadays, the advanced methods such as 3D scanning and 3D modeling and 3D printing methods are coming up, and then they are getting more and more popular because of its widespread application and ease of fabrication. When it comes to suspension systems, you have harness suspension systems, anatomical suspension systems, and suction suspension systems. So the harness suspension system uses belts and harnesses, and whereas anatomical suspension uses anatomical features of the residual limb to mechanically lock the socket in place. When it comes to skin fit suction, under suction fit, there can be issues with regard to actually having a proper suction effect. But with roll-on liners, such as distill locking mechanisms, liner fit suctions, and hyperbaric suction methods have proved to be much more effective when it comes to keeping the prosthetic in place in the socket within the limb. And in overview, basically you have the following input devices to select from. So there are multiple number of sensors to select: the potentiometers, encoders, EMG sensors, torque sensors, IMU sensors. So there are variety of different sensors that you can pick from. The transducers, such as pressure transducers, load cells, and FSR-based transducers, are commonly used in these different devices that I speak of. And in addition to that, even mechanical switches are also used. The actuation methods are basically electric, pneumatic, hydraulic, and combination of electric, pneumatic, hydraulic. So but mostly it has been seen that electric actuators have been utilized in these most of these bionic devices. So the powering methods that have been identified in these devices are some of them are passive, some of them are body powered, and in particular Bionic Limbs externally powered. Now, the battery technology has developed over the years. Lithium-ion batteries are the most selected option among the different options. You have lithium polymer options as well nowadays, but with improvement of technology with high energy density, lithium-ion batteries are still in there. He's making a huge impact in the market. When it comes to materials for Bionic Limbs, you have metals, polymers, carbon fibers, and other types of supporting material that you can select from. Especially titanium has a huge role to play because of its high specific strength. So strength to weight ratio is higher. And then polymers are also playing a major role because of the 3D printing technologies now developing, and polypropylene, polyurethane, and PVC are also being used in the preceding decades. The carbon fiber is a nice addition. It is similar to titanium. It is coming up in the market and heavily being used in the production of sockets and prosthetic structures. And supporting materials, pencoporon and other types of material to provide that lining between the prosthetic socket and the human is also considered. And then you have manufacturing methods. There are three to speak of: the subtractive method, the computer-aided manufacturing, and CNC machining in particular. The additive manufacturing process is very much there to stay for. It is the fourth industrial revolution, and then molding and forming are still used all parts of the world for the purpose of developing the prosthetic sockets in particular. So in general, the target here, when it comes to developing bionic limbs, would be you need to come up with an affordable solution. It has to be functional. It has to be lightweight. It needs to adapt to situations. It has to be ergonomical. And of course, it has to be safe. And it has to provide natural movement capability. It should be able to use all day and for all purpose. And it should be durable. You should be able to use it for under different circumstances, submerged in water, probably in heavy rain, so or very humid or very hot environments. And then easy to control, easy to maintain. Likewise, you can think of all the possible reasons that you need to target for when it comes to designing your own prosthetic devices in future. So the idea here from Hugh Herg, achieve biological functions. Basically, you try to achieve biological functions, but don't stop there, go beyond. So that would be the take-home message from my end. And thank you for your patience with the extended time that I've taken.
Thank you very much, sir. So we have some questions. Most of the questions were answered during the presentation, so I'm not going to ask those questions again. But we have some questions like, One has asked, what are the inbuilt safety features in these devices if there are mechanical or other failures?
Yes, usually that has been the most concerning situation actually, most of the time. That is why most of the devices are still not there in the market because of the safety issues that normally they have. Usually, yes, you need to have the mechanical limits to ensure that the limb does not bend beyond a certain limit that would cause instability. So that is a typical consideration when it comes to designing prosthetic, not only prosthetic, even exoskeleton, so powered orthesis. Of course, you can actually divide them into two categories, these safety features, mechanical safety features as well as electronic and control end, you can have safety features. And of course, some of the devices, if there is an electronic failure, so the sudden collapses are prevented with mechanical locking systems. So you need to have some contingent plan to provide that safety. Usually, in most devices, what you find in commercial means have these types of features.
Thank you very much, sir. And we have another question, what power sources and how those are used in a compact way in prosthetics?
Yes. Now it has to be portable. That is the main issue. Now you cannot use a tethered power source. The idea is to use this outdoor purpose. So when it comes to selection of power sources, typically battery packs are being considered. Battery units are being considered. So the battery technology has evolved a lot. Now you have nickel cadmium batteries earlier being used. And then nowadays we have lithium ion batteries being used. Right, so you have lithium polymer batteries. Now lithium metal batteries are also there, and then nickel metal hydride batteries are also there. So there is a plethora of battery options available. With the advancement of technology, nickel lithium ion batteries are becoming smaller in size. They are, and then energy densities are improving day by day. So still, it's being improved. So there is room for improvement. So we can expect the battery technology to improve quite fast because of the consumer electronic industry, not just the bionic industry, but also the other consumer industries need the use of batteries. So we would expect within the next 4 to 5 years a very huge improvement of battery technology, which can last for days. Even some of the commercial devices that I presented in my talk, in fact, they can be used throughout the day. So with battery packs that are inserted into the device, so they can be made compact and they can be used for a longer period of time. So that problem is being sorted out actually from a technological point of view.
Okay, thank you very much, sir.
Okay.
I think that's with today's time. That's only we have time for questions. And okay, actually one more question is there. Lower limb suction system has problem with sweat. What is the solution for this? Limbs are not stay after suction because of sweat. So can you give a brief answer to this?
Right. Yeah. Now there are now if you are using skin fit suction, probably as the muscle volume change, so the socket can get released because there is no proper seal. So probably this cannot be sorted out. That may not be possible. So so liner-based suction technologies you could consider. I'm not sure whether you are using liner-based technology. So there is the option of using these gel bands about the liner, which can provide a better seal, right? Now, this particular technology, if you notice, probably you can go back to my presentation and have a look. So they are referred to as the hypobaric suction method. So for this, you need to use roll-on liners. And then, of course, I suppose this is for the upper limb case. So if it is for the upper limb case, then I don't think distal locking mechanisms can be used. If it is for the lower limb, yes, you can also consider using distal locking mechanism. Probably lanyard strap method can also be considered. If not, I suppose better to use hyperbaric suspension method.
Okay, thank you very much, sir. So for questions regarding the control of bionics using biosignals, we will be having the sessions tomorrow. So the questions that you have asked today will be answered tomorrow if they are regarding the biosignals. Thank you very much, sir, for a nice presentation.
Thank you very much, and thank you for bearing with me.
Yes, sure.
You're right. Thank you. Now, the design challenge, I'm sure you have already got this document. However, let me make a brief explanation quickly as possible. The task is the design of a functional finger prosthesis. So you can see here the middle finger of this person has been amputated following an injury. So the entire finger is missing, right? All the other fingers are functioning normally. And then this particular amputee is a 35-year-old male that fits the 50th percentile of a male population. Now you can get an idea of what the dimension should be for a 50th percentile male subject if you refer the anthropometric charts. So that's a heads up for you. And then amputee by profession is a carpenter, and then mainly rely on dexterity of the hand to perform the woodworking task. So you can see how important it is for this person to have the middle finger to perform the task. So you need to consider this also when it comes to designing a prosthetic finger, not only to support the activities of daily living, but also his trade. You need to be able to support with your proposed or prosthetic finger. The amputee hopes to use the finger prosthesis for both domestic and trade-related activities. So that's basically the background for you. And then deliverables should be prepare a graphical representation of the design. Now, those who are used to the CAD platforms, you may use. It doesn't matter which type of platform you use, what type of software that you use. As long as you present the details, you need to also provide us with the CAD model, and then also it should be in a universal file format so that we are able to actually have a look at the model and get an understanding of your work. If you're not having access, or if you don't have any experience in using CAD platforms or CAD software, don't worry, we will not be harsh on you. We will consider your ideologies that is conveyed through freehand sketches with labels. Make a very good communication through the use of freehand sketches, which has been the case before the advent of the CAD systems. So we will also consider that. Okay, so you may use both. If you like using both CAD technology as well as freehand sketching, you may use both. So whatever way that you prefer, you go ahead and give us a graphical representation of the design. Explain the working mechanism of finger prosthesis, including details of the mechanical and no control hardware. So you'd have to explain yourselves how the finger mechanism is going to work. You can also actually do so with the use of the CAD model. If you can simulate or animate, it is another way how you can. But by using freehand sketches, you can actually draw individual steps of the mechanism, how the process is going to work. So you have to make it fairly clear to us so that we can understand and assess. And then describe design considerations for developing proposed finger prosthesis. So all the different design considerations that you have thought about. So I have made a discussion, a very lengthy discussion today about the considerations that you need to have for the development of prosthesis. So you take a leaf from that. You also do some self-reading and do make your own description on how you plan to develop in the sense, because the next stage is to fabricate the prosthesis and then use it on a person. That would be the next step. So for testing purpose, and then basically you will turn it into a product. So this is what you call the development process. So you need to explain the entire process, what materials you are going to use, what manufacturing methods you are going to use, and what selections you have made, what sensors and what actuators if you are going to use, what if it is body powering method, what body powering method, in what way it is achieved. You need to be able to explain everything in detail here. Okay, so and if I go to the final slide, so you are given 2 weeks. This is complete, right? So you can put everything in a Google Drive and then send us the link so that we can access those files and then do the assessment. So if you have any questions, I'm all ears. Go ahead.
If you have any questions, you can post it on the chat regarding the challenge.
I think one participant isn't able to see it. We will be reposting the PDF on the chat. Thank you, Pramit. So please download it and refer to the instructions. You will have the submission link there as well. I believe with this, we have come to the end of today's sessions. And once again, I would like to thank all of our speakers, our panelists who have joined with answering questions, our moderators with handling the Q&A sessions, and also our organizers from the Makerspace end. Thank you very much, everyone. I'd like to hand over today's meeting controls back to the Makerspace team. Thank you very much.
Okay, thank you very much. And ladies and gentlemen, thank you very much for the amazing session and also for your valuable time and the effort throughout this session. And I know you're really busy with your busy time schedules. Actually, that was amazing, incredible session. We learned a lot more things from the Bionic Limbs and innovations that taking place. And thank you very much, Professor Rohan Gopura and Engineer Prabhudev Ratnavira. It was an amazing session. We learned a lot from you. Thank you very much and have a good day. Thank you.